we have seen that the spin state A can be represented as a column matrix A1, A2, and this we call a spinner. And it is to be expressed in terms of the basis vectors, which were up z was 1, 0, and the down z was 0, 1. And then this vector has to be normalized and things like that. That's something that we did in the last class. Okay. Now you have then notice that this representation is different from a wave function representation because the spin is not represented by the wave function. So we are now not talking about the Hilbert space. We are talking about the spin space, where these two-dimensional vectors are all possible two-dimensional vectors are the neighbors. Now, the spin space, you have each spin vector like this. And we knew when we did the wave mechanics, we knew that we have a wave function and we have operators. Operators operate on the wave function to give a different function, and so on and so forth. And if you perform an experiment to observe some observable, then you can only observe the eigenvalues of that operator. In case of spin, therefore, we need to define similar operators that can operate on this kind of vectors to give different vectors. And it is obvious that if these vectors are two-dimensional, the operators will be nothing but 2 by 2 matrices. So we now go to the operators in spin. Now, what would you like to observe? For example, using the Stern-Gerlach apparatus oriented in the z direction, we are trying to observe the spin in the z direction. Therefore, the spin in the z direction is an observable, and there has to be an operator. As with all observables, there will be an operator. So there has to be an operator that is related to the spin observation in the z direction. So it will be SZ operator. Similarly, if the Stern-Gerlach apparatus is oriented in the x direction, you would like to have a observer in the x direction. So S. So we'll need to obtain these also. Depending on in which direction things are to be measured. Now, let us start with the z direction, because normally the way we have sort of laid out the experiment, our orientation of the magnetic field was in the z direction. So let us work that out first. We have seen that if this is the vector up z, then that means a spin preparer where the magnetic field is oriented in the z direction, the output coming out of that, one part of it has been blocked. The one that is going down has been blocked. The one that is going up is allowed to pass, which means that it has been prepared in this state. So if it is prepared in this state and we observe it by another Stern-Gerlach apparatus oriented in the z direction, then all the silver atoms will go to the upper spot, which means that they will have a magnitude of the spin angular momentum plus h cross by 2. This observation essentially means that this is an eigenvector with eigenvalue okay. And similarly, if you have something that is oriented downwards, that's also an eigenvector with eigenvalue minus h cross by 2. That means if it is prepared in this state, then with probability 1, all the atoms go to the upper spot. If it is prepared in this state, then with probability 1, all the silver atoms go to the lower spot. Okay. Now this essentially means, let me erase this and let me continue. This from here. So this means that that SZ operating on the up Z should give the eigenvalue times up Z. Okay. This means the eigenvalue times 1 0. Okay, that is the expression for this matrix. Similarly, SZ with the character that if it operates on down Z gives minus h cross by 2 as eigenvalue down Z is equal to minus h cross by 2 0 1. Okay. Then we are trying to find out what operator is this. Let us say this operator is, let us work it out here, is ABCD. A, B, C, D. Operating on, this is 1 0, 1 0, is giving me h cross by 2, 1 0. That immediately gives me A times 1 plus B times 0 is equal to h cross by 2. So A is equal to, okay, and C times 1 plus D times 0 is, C is then 0, right? Similarly, from this equation, you have A, B, C, D. It is 0, 1 is equal to minus h cross by 2, 0, 1. This gives you B is equal to 0 and D is equal to, so it is then clear that the SZ as a matrix is, give some space here, because I have to write h cross by 2. H cross by 2, it is 1, 0, 0, minus 1. So it was easy to obtain the operator for SZ. It is not that straightforward to obtain the operator for Sx, Sy, but we can follow certain logic in order to obtain that. Let me delete this part and then continue. We can, I suppose, also delete this part. Done. uh, we know that the orbital angular momentum, the angular momentum, orbital angular momentum in the three different directions do not commute with each other. Uh, and we have a relationship like Lx Ly minus Ly Lx is equal to I h cross L z L y L z minus L z L y is equal to I h cross L x and L x L y minus L y L x is equal to I h cross L z. So these are the equations that we had earlier obtained in terms of the orbital angular momentum. Now, Wolfgang Pauli assumed that the spins also obey the same kind of relationship. The spins in two different directions would not commute with each other. And there's the indication of that coming from the Stern-Gerlach experiment that I already hinted at, because if you have a spin preparer in the z direction, and then it goes through another spin preparer in the x direction. That means it has been. Let me just draw schematically. We had seen that if there is a Stern-Gerlach in the z direction, there are two beams coming. One is blocked off. Then it goes to another Stern-Gerlach. In the x direction. Again, there are two beams coming. One is blocked off. So here, it has been prepared in the up z direction. It is up z direction. Then when it goes through the x direction, then basically if you allow this to pass, then it will be half in the. So it is this will be half the component and this will be half the component, up and down. But suppose now we block it off and allow this one to pass to another Stern-Gerlach apparatus. Again in the z direction, then you will find that this will be now it is again it will be half and half, which means that even though it was prepared in the up z direction, when it is again prepared in the up x direction, that means you make an observation here, and the moment you are blocked off, you essentially have made the observation that all it just collapsed to the state up x direction. So this is up x, and that erases the information that was created earlier, which means that these two directions must be non-commensurate. So they should not, the corresponding operators should not commute with each other. So this again indicated that there has to be a similar relationship between the spins. So he assumed that the spins will also assume a character which is sy minus sy sx is equal to I h cross sz, and so on and so forth. That means similar relationship between the spin observables. And further, you have to assume that all these operators corresponding to observables must be Hermitian, because that's one requirement of anything to be observable. The eigenvalues has to be real. So plus the Sx, Sy, Sz must be Hermitian. And then using these and the fact that it must be Hermitian, he worked out the Sx and Sy. Uh, I will not exactly work out the Sx and Sy in the way, because that is a bit lengthy procedure. What I'll do is I'll simply write Sx and Sy and then check that they follow these characters. Okay, so let me erase and write it here. You can also erase this. Let me write it in one shot, all the three. What I found was that there's only one solution to this situation, where the demands are placed, and this is h cross by 2. It is 0, 1, 1, 0. Obviously, it is Hermitian. The diagonal terms are real. The off diagonal terms are, I mean, they are also real, so the complex conjugate does not matter. Sy is equal to h cross by 2, 0 minus I 0, and Sz is, as I wrote earlier, h cross by 2. It is 1, 0, 0 minus 1. Well, now I will leave it to you to check that equations of this form are satisfied. You just check whether these kind of equations are all satisfied with these matrices. And it is obvious that this is a Hermitian matrix, because the off diagonal terms are complex conjugate. Here also that's true. So the Hermitian condition is met, and the additional condition that had to be checked is this. I leave it to you to check it. These matrices are called the Pauli matrices. Okay, is it clear how the Pauli matrices are obtained? Okay, so these are the Pauli matrices, and if we apply these matrices on any arbitrary spinner, then the spinner will change to some other direction, and the eigenvalues of the matrices are the things that you observe. So eigenvalues are h cross by 2. So that's what you actually, h cross by 2 and minus h cross by 2. These are the things that you actually observe. Uh, Now we have worked out the spin vector in these directions. These are the basis vector directions. But suppose I want to observe in some arbitrary direction. So, for example, if you have, now let me delete this and make some space. I want to do it. I'll do it in a better way. And suppose there is a vector. Badly drawn. Oh, I'm here. Okay, and here for this a vector, and this will be the vector that we are trying to plot, and some arbitrary direction, say n. This is what we are trying to figure out. And then we'll drop the perpendiculars, and we'll have this vector, and we'll have these. Great. And this is our theta angle. This is our phi angle. So on that basis, we can work out the vector n. So, and if you have any particular another vector s, say another vector, say s, you can think of drawing a projection onto n, and if the thing is in state s, and I have oriented my Stern-Gerlach apparatus in any arbitrary direction n, then we'll be able to find out the probabilities that way. So this is what we are trying to drive at. The spin is in any arbitrary direction, and I have oriented my Stern-Gerlach apparatus in another arbitrary direction n, and we are trying to figure out the probabilities of finding up and down. So in that case, let me delete this also, make some space. Then the projection is n dot s. It is actually s cos some alpha. Alpha is the angle between the two vectors. And the n vector can be expressed as expressed in terms of the basis vectors. So let us call them the ex, ey, ez. So in terms of those basis vectors, it becomes the z component will be cos theta and sin theta, cos phi, and sin theta. Okay, yeah. So it is x component is sin theta, cos phi, ex vector plus sin theta, sin phi, ey vector plus cos theta, ez vector. Okay. So then we can calculate this. It is the projection of s on n is n dot s. Then it will be sin theta cos phi. This will be the projection in the direction of x. So it is sx, let's write it as sx, plus sin theta sin phi. It is sy plus cos theta sz. Now, normally, when we did such things earlier in wave mechanics, wherever we had some observable quantity, we replaced that by its corresponding operator. So, for example, when we had p square by twice m, we replaced the p by its operator equivalent minus is cross del x and proceeded. So if you want to convert something into its equivalent operator, we write it out and convert the components into their equivalent operators. Here I see that Sx, Sy, Sz are such things. So in order to obtain the Sn as an operator, we will have to put all these operators around here. Okay. So then Sn, what does it signify? It signifies that I have my I'm trying to figure out the operator that will tell me the spin component in the n direction, because my Stern-Gerlach apparatus is oriented in the n direction, any arbitrary n direction, and my spin vector is in s direction. So this has to be obtained, and that is then expressed like this. So Sn is then obtained as this is here, and this is here. We'll substitute here. It will give me h cross by 2. It is sine theta cos phi, and this one is 0 1 1 0 0 1 1 0 plus sine theta sine phi. This is 0 minus I 0 plus cos theta. This one is 1 0 0 minus 1. Give a line here, separately, and the bracket is closed. And if you simplify this, it is easy to simplify. Then you will get h cross by 2. This term will be 0, this term will be 0, this term will be cos phi. This term will be sine theta cos phi. This term sine theta minus I sine theta sine phi. And this term is 0. So sine theta comes to common. So I will write sine theta. And cos phi minus I sine phi is e to the power minus I phi. Here it will be same sine theta cos phi plus sine theta sine phi I. So it will be sine theta will come common, sine theta, and it will be e to the power I phi. And this term will become, all these are 0. This is minus cos theta, cos phi. Cos theta. Cos theta is okay. This one is okay. This one is no cos theta. This one will be cos theta. Okay. So this is the general spin matrix. Spin matrix where we are talking in terms of projecting spin any arbitrary s direction into an arbitrary n direction. So in that case, sorry, what's happening? Kill all this junk. Sometimes the pen tablet behaves in a peculiar way. All right, and you would notice that if the way we have oriented the Stern-Gerlach experiment, y direction is the direction in which the beam goes, which essentially implies that my phi is 0, and if the phi is 0, then it reduces to, for phi equal to 0, it reduces to, that means if things are in the xz plane, then Sn becomes simply sorry, h cross by 2 I have to write. it simply becomes cos theta sine theta, here also sine theta, and here it is minus cos theta. Right. Okay, so this is the general spin matrix uh, where I am considering that the Stern-Gerlach apparatus is oriented in any arbitrary direction n, then the spin matrix will be this. Okay, provided phi is equal to 0, which means that the flow direction of the beam is in the y direction. Okay, so let us continue with it. Now the question is, okay, let me delete this now in space. Let us delete this and let's keep that. Okay, let's skip this. Huh? So this is S in general is matrix, and this is the particular matrix for a particular direction of the beam. Now the question is, what are its eigenvectors? Right? Uh, that means this is the general spin matrix, its eigenvectors. So it should be such that the Sn operator operating on that eigenvector in the n direction should give me either plus h cross by 2 up n, or the same spin operator operating on down should give me minus h cross by 2 down. Right? Now, again, I will not go through the long route of actually deriving this vector, but I will just write it and you can easily check that it satisfies this equation. I'll write that it gives up n. So the way to derive it is this put here, and what should be this, so that this condition is satisfied. So it is not very difficult to derive, but I'll just write it and you can check that it actually satisfies. It is actually a column vector of cos theta by 2 e to the power I phi sine theta by 2. This is the up one, and the down one is minus e to the power I phi sine theta by 2, and this is cos. You can very easily check that you put this one and this one here and simplify this, you will get this. So it's very easy to check, so I'm not cracking my head to that. Well, if you want quickly to check, it is like this. So it is Sn operating on this n, up n vector, is this h cross by 2 cos theta, here sine theta e to the power minus I phi. This is sine theta e to the power I phi, and this minus cos theta. This is cos phi, no, cos theta by 2. Theta by 2. This is e to the power I phi sine theta by 2. If you put, then cos theta by 2, sine theta, sine this. So ultimately, you will put cos minus sine. It will lead to basically cos A minus B. So that will lead to exactly the same form. Okay. So cos A minus B is equal to cos A cos B plus sine A sine B, and so on and so forth. You just put that, and then you will find that this is nothing but minus h cross by 2, which was here, times this vector. So it is easy to actually check. Good. So we have, in addition to this, we have obtained that these are the two spin vectors in the arbitrary direction n. Okay. Let me kill this. I need to delete, get more space, so I'll just delete it, and if necessary, I'll write again. Okay. Now the idea is that if a particle is prepared in such a way that it has a definite value in the direction n, then if it is measured in the same direction, that means another Stern-Gerlach apparatus is oriented in the same n direction, it will show plus, or if it is depending on which beam is blocked, it will show minus or plus. So which means, but if you orient the second Stern-Gerlach apparatus in any other direction, then it will not be a certain result. If it is in the same direction, it will be a certain result with probability 1. Either everything will go up or everything will go down. But if it is any other direction, then it will not go in a particular direction. So we have already obtained the Lx, Ly, Lz, Ly, sorry, Sx, Sy, Sz. Sx, Sy, Sz. Now, there is another similarity we'll draw with the orbital angular momentum. In the orbital angular momentum, we obtained another thing, that is L square, right? And what was the result? Our L square was Lx square plus Ly square plus Lz square. And by converting that into the equivalent operator form, we wrote it like that, and we obtained L square as an operator. And we found that L square commutes with Lx, Ly, and Lz. These are the results that we found for the orbital angular momentum. Now, again, Pauli assumed that spin also behaves in the same way. So S square commutes with Sx, Sy, Sz. So let's talk about what S square is. So it is sorry, I'll write S operator square is Sx square plus Sy square plus Sz square. So we need to obtain each of these. So let's quickly obtain each of these. So Sx square is h cross by 2 square, so h cross square by 4, and this is if you just work out, it was 0, 1, 1, 0, 0, 1, 1, 0. This will give you just the identity operator. Okay, so h cross by 2, let's go by 4. It will be 1, 0, 0. So it is h cross by square by 4 I operator. Okay, and if you do all these, sy square h cross square by 4, it was again 0 minus I 0, 0 minus I 0. Again it will get h cross square by 4, the identity operator 1 0. So all these are essentially the same thing. It yields the same thing. Sorry, not square. Similarly, sz equal to same thing. No? So sz square is h cross square by 4 I, which means that if you add them up, your s square uh, becomes thrice h cross square by 4, not I square, by into I. Okay. This is interesting because h cross square has the same value, and you would notice that every spinner will be eigenvector of a square, every spinner. So just apply the a square on any arbitrary spinner AB, you will get 3h cross square by 4. I operating on AB will give AB. So AB is any arbitrary AB is an eigenvector of a square with an eigenvalue of this, right? Now the interesting part. We had earlier assumed that the spin value of the electron, because I told you that what you are ultimately measuring by measuring the spin of a silver atom, you are essentially measuring the spin of an electron. We assume that it is h cross by 2, but now we see why it really comes about. In case of the orbital angular momentum, we saw that L square has eigenvalues. It was L plus 1 h cross square, right? And then we assume that S square also has eigenvalues S plus 1 h cross square. Just arbitrarily we assume and see what that results in. Then what should be the S so that the result is this? That's the question we ask. If S square also follows the same kind of a rule, then what should be S so that we get this as the eigenvalue? You will find that it is basically if you put half, then half plus 1 h cross square is equal to essentially 3 h cross square by what you had here. So only if you assume S to be half, you get this result. And that's exactly why it sort of matches our assumption. We had assumed that S is half, and it actually matches our assumption. And this is one of the reasons why people say that the electron is a spin half particle, because its possible angular momenta would be h cross plus h cross by 2 and minus h cross by 2. So the values of possible values of S square is this the eigenvalue. Possible values of Sz, the z in the spin in the z direction, are we write it as in the same way that we wrote the angular momentum eigenvalues in the uh, orbital angular momentum case. We wrote it like this. We write in a similar way. If we write in a similar way, we see that ms can have values plus minus half. This S is a spin quantum number and ms is a spin magnetic quantum number. So ms is all right. Before we end, a slight time is available. I will explain something that is a bit might be a bit difficult to grasp because it is so very counterintuitive. But I have to see, when we were talking about the double slit experiment, then we said that the electrons that pass through that can fall in various places, but before it actually strikes the screen, each electron is in a superposition of various possibilities, and ultimately when it strikes the screen, one of the possibilities actualizes. Now here also a similar thing happens. I said that if you have a Stern-Gerlach apparatus and there are two beams that are coming out of it, actually these lines are actually misleading. These lines are actually should not be drawn. It is only drawn for the sake of convenience because sometimes we want to block off one path. But it does not really travel in a line like this. It doesn't have a trajectory. It basically travels, and when it strikes the screen, then it has various probabilities of striking. And depending on the probability, some will go up here, some will come down here. And the number that falls here and the number that fall here are given by that cos square theta by 2 rule. And so ultimately, when it actualizes, it comes here. This is the standard Copenhagen interpretation, that it is in a superimposed state of both the possibilities. Each atom is in a superimposed state of all the possibilities until an observation is made. And when the observation is made, it is basically when it strikes the screen and when its travel basically ends. And then it actualizes either here or here. But before that, the notion, the mental notion that some of them are traveling like this and some of them are traveling like that is something that the Copenhagen interpretation does not permit. But I should also tell you that many scientists are uncomfortable about this Copenhagen interpretation, which says that the state of the particle is undecided until you make an observation. By the way, suppose I have now blocked off this path and allowed only this path to go. Then have I made an observation? Yes. If you have blocked off a path, which means that the particle had to take a decision as to the spin, whether it's going up or down, and therefore at this point you have made an observation, and therefore just before that it is in the superimposed state of both the possibilities, but at this point, just after this, it has collapsed to the up z state. So here, when it's coming, it is actually a linear superposition of upz and downz state. But when you have blocked off one path and then you have made a measurement, you have made an observation, it has forced it to collapse into a upz state. When you have another Stern-Gerlach apparatus and orient in the x direction, then you have essentially, again, two beams emerge, one you block off. The moment you blocked off, you have forced the other one to be in the up x state. So these are also observations. And finally, the observation is made here. So if there is an irreversible event happening, irreversible event like the silver atom striking a glass plate, or some silver atoms being blocked off by something opaque, striking here, and therefore causing something that is irreversible. And whenever that happens, the beam actually collapses. Okay, this is sometimes a bit difficult for students to appreciate because there is no analog in day-to-day world. So it's difficult to appreciate. But well, the majority opinion of the scientists is like the Copenhagen interpretation, though scientists are trying to work out other possibilities, or people are trying to figure out what makes a wave function collapse or a spin state collapse. There is a lot of work going on right now. Clarity is not yet there. But so long as clarity is not yet there, the best possible option is to believe in the Copenhagen interpretation, which says that the particle takes a decision as to where to strike when it has reached the striking point. Before that, it does not take a decision. It is in a superimposed state. So it is not that it is traveling in a particular way and striking it. It is actually everywhere over a range. And then it decides, it sort of, the moment it hits it collapses into either this or that, with a probability that we'll calculate soon in the next class, with a probability that this says how many of them will collapse here, how many of them will collapse here. Okay, fine. So let us stop the class today. And yeah,
Excuse me, sir.
Yeah, sure.
Sir, I have a doubt here. It might be very naive, but just wanted to ask.
Nothing is naive. Yeah, carry on.
Sir, so we said that there is nothing called as specified trajectory in quantum mechanics.
Yes.
So when we are obstructing the path here, we're essentially making whatever state the electron, the silver atom was in, we are making it collapse in the middle where we obstructed its path. So there also we should see two spots, right? Because we don't know
where here
the place the place where we obstructed the path. So we don't know whether the silver atoms following this trajectory, actually they are not following the trajectory. Okay, just for the sake of convenience. So whether if they are following this trajectory, are they in all of them following this trajectory or in the down state?
You are saying whether a particular atom is here or not, right?
No, I'm saying that we don't know that the silver atoms following the trajectory represented by the lower curve are all of them are in the down state.
Yeah, that you know. That you know,
Yeah,
because here there was a magnet and it has passed through. It has passed through, and we have placed a blocking at some place which has blocked the lower, and the moment you have blocked it, the upper one collapses to the state. Okay.
Yeah.
But you do not know where the particles are, or not where the particles are. You can find that out, but what the spins are. But the moment you have made this observation also collapses into this state. That means all the remaining atoms become in this state.
Sir, we just placed an obstruction in the path. So how does the silver atom decide that only the downspin will be blocked and the upspin will pass through?
That is the peculiarity of quantum mechanics. Because this one, that means you're blocking half the path, is essentially
Sir, we don't know the trajectory, so we may place the obstruction anywhere. We don't know the trajectory, right?
We do not know the trajectory. That's true. But
so we place
but imagine it this way: that we take a plate and slowly move it up. Okay. At some point, we'll find that there are dots coming here, and so we know we have blocked at least one path. If we take it up here, there will be two dots. That's the classical, the first Stern Gerlach apparatus, right? If you place it here, but we now take it up to a certain level, so that we have only intercepted one of the dots, and the other we let it pass. The moment you've done that, that's also an observation. An observation collapses the wave function. Get the point?
Yes, sir, but I'm only
They're,
half
they're
convinced.
very difficult to fathom, because there is nothing like a analog in a day-to-day world. This is peculiar behavior. I told you, started by telling you that this is a very peculiar behavior, and still we have to come to terms with that. But this is nothing special. This is something that happens in the normal double slit experiment also. If you block one slit, the behavior completely changes. What does it mean? You have made an observation right there.
Yes, sir.
Okay, so it's difficult. I understand that, but I mean, we have to slowly come to terms with it. But as I told you, that the whether the Copenhagen interpretation is correct or not, we do not have yet a clarity about that, even after 90 years of existence of quantum mechanics. Maybe while when you are mature scientists, will have some kind of clarity. Okay. Okay, let's stop today, and we'll continue in the next class.